All right, welcome to the Explainer. Today we're going to talk about a new theory of physics called unified dynamics. And when I say it's radical, I mean it is really out there. It's a theory that's making waves, not just because of its successes, but because of the sheer audacity of what it claims.
So think about our best description of the universe right now, the standard model of physics. It works beautifully, but it has this, let's call it a dirty little secret. It's built on 19 fundamental constants. These are just numbers, like the charge of an electron or the strength of gravity, that we have to go out, measure, and then literally plug into the equations by hand. The theory itself has no idea why the numbers are what they are. Okay, so here comes unified dynamics, or UD, with an almost unbelievable claim. It says that everything, all the forces, all the particles, the constants, even the fact that we live in 3 dimensions, it all just emerges from the pure geometry of one simple shape, the tetrahedron. And get this, it claims to do it with 0 free parameters. That means no plugging in numbers. Every constant in the universe should just fall right out of the geometry itself.
Okay, let's really get into this. The core idea is that the tetrahedron isn't just some pyramid. No, according to this theory, it's a kind of engine, a unique machine for generating physics. Its symmetries, its angles, its properties, that's the supposed source code for reality.
So you can kind of picture it like this. In one corner, you have the reigning champion, the standard model. It's complex, it's built on these intricate mathematical groups, and it needs those 20 or so numbers we have to feed it. And in the other corner, you have unified dynamics, claiming to get all that same complexity from one single, simple object. It's a real battle between complexity and radical simplicity.
So, how does a theory like this even begin to prove it's not just a fantasy? Well, it goes straight for one of the biggest, baddest, unsolved problems in all of math and physics, the Yang-Mills mass gap problem. This is a huge deal. It's basically asking why the strong force that holds our atoms together is so strong but only works over tiny distances. It's so important that solving it comes with $1 million prize.
Now, UD doesn't just offer a vague idea. It lays out a formal, rigorous, 12-step mathematical proof. You can see the flow here. It starts by defining its whole system on a fractal grid made of tetrahedrons. Then it walks through, step by step, proving key properties, until it finally demonstrates that a mass gap, that little buffer that keeps the force from leaking out, must exist.
And this isn't just a concept. It spits out a hard number. The theory derives that this mass gap has to be at least 3 divided by pi. And this number isn't just pulled out of a hat. It drops directly out of the most basic geometric properties of the tetrahedron itself, things like its curvature and its mathematical Hodge spectrum. It's pure geometry leading to pure physics.
Now here's the crucial part. A lot of cool ideas work in a simplified little model, but then they just fall apart when you try to scale them up to the messy, continuous, real world. But UD has an answer for that. Because of a specific geometric growth factor, about 1.53, which is baked into its fractal structure, the mass gap doesn't disappear. It actually survives the leap from the clean model to the continuum of reality. So, the abstract math seems to hold up, which is a huge step. But this is where it gets really compelling, because beyond the proofs, unified dynamics makes some shockingly precise predictions about the actual, measurable constants that run our universe.
And this table just lays it all out. It shows several of those fundamental constants as predicted by UD right next to the values we've measured in experiments for decades. And just look at the numbers. The fine structure constant, the weak mixing angle, the tau to muon mass ratio. The theory's predictions are off by less than 0.5%. That is stunningly accurate.
And this, right here, is the mic drop moment for the whole theory. Remember, these numbers are not tweaked, they aren't adjusted to fit the data, they fall straight out of the math of the tetrahedron. There's really nowhere to hide. The numbers either match reality or the whole thing is wrong.
This all sounds incredible, but how in the world do you test a theory of the entire universe? Well, you do the next best thing. You build a digital copy of that universe inside a supercomputer, and then you do everything you can to break it.
And that's where this thing, Oscar, comes in. You can think of it as a digital laboratory for UD's universe. It's this massive simulation that builds a universe on that fractal tetrahedral lattice and then just calculates how it's supposed to evolve based on the theory's rules. So the researchers set up these huge simulations with systems of up to 65,000 different points. And then they just started injecting random noise everywhere. The theory calls this burden, and it's meant to be like the chaotic quantum fizz of the real world. The big question was, Would the orderly patterns predicted by the theory survive all this chaos, or would they just get washed out?
You know, the centered thinking is pretty simple. If you add more noise and randomness, you should just get more chaos. You'd expect any clear signal to get drowned out. But that is not what happened. In fact, something totally opposite and completely unexpected started to happen in the simulation.
This slide shows the mind-blowing result. This chart is basically a measure of signal clarity. On the left, in a perfectly clean, quiet system, the signal is super weak, almost nothing. But then look on the right. In the noisy, chaotic, burdened system, the signal suddenly becomes more than 20 times stronger. Order was literally emerging from the chaos.
Again and again, on different scales, the Oscar simulation kept returning this one single word to describe its findings: anomalous. Now that doesn't mean it's an error. In science, that means the result is real. It's statistically significant, and our current understanding of physics simply cannot explain it.
But let's be real. For any new idea to be taken seriously as a scientific theory, it can't just be a highlight reel of its greatest hits. It has to be upfront about what it gets wrong. And most importantly, it has to be testable. You have to be able to prove it's wrong.
And what's really impressive is how open the theory is about its current problems. For example, its prediction for the Higgs boson's mass ratio is off by about 2.5 times. Same goes for a value that governs how particles decay. This shows the theory is powerful, for sure, but it's also a work in progress. It's incomplete.
And this is exactly why this whole thing matters to science. UD makes clear, bold predictions that can be tested in the real world. For example, if scientists ever discover a fourth generation of particles, or if they ever find that a proton can decay, this theory, as it's written today, would be dead in the water. Proven wrong, period.
So what are we left with? We have this incredibly formal, mathematically dense, and shockingly predictive alternative to everything we know. The monumental task for the scientific community now is to figure out if these incredible successes are a true peek behind the curtain of reality, or if it's all just a stunningly beautiful and elaborate mathematical coincidence. The real investigation is only just beginning.